the defense, and then yeah.
Great. So is everyone here?
Yeah, I believe
Yeah.
so.
We only have 3 in the committee. Yeah.
Great. Okay, great. Well, then as chair, I say, Jason, take it away.
Thank you. Yeah, so thank you all for being here. It's really exciting that I get to do this and share what I've been working on over the last year, really, starting with an independent thesis last year. So let me enter slideshow here. And I just want to mention that a lot of the things, there are some aspects of gauging the x-cube model, which is the model we'll cover of fractons, an aspect of both the tensor gauge theory as well as the fracton field theory have been reduced. We can either, if anyone has any questions, I can pull up extra slides or go directly to the thesis. So just making that clear from the start. So the first thing we're going to do is talk about the motivation for the work and how it was originally uncovered. And the best place to start with that is actually the toric code, because the history of the toric code very much feeds into the history of the x-cube model, in the sense that the fractons more generally were conceived in the same spirit, in the sense that going off of Feynman's kind of original dream for a quantum computer and the kind of second quantum revolution that came in the late 90s with regards to quantum computing, Kitaev started to blend the field of quantum mechanics and quantum computing with condensed matter in his toric code, which we'll cover in the next slide. So the toric code is defined as a Hamiltonian with the following terms. A vertex term, which consists of Pauli X matrices. So these tau, the tau will be reserved for what are called gauge fields, and sigma later on will be reserved for matter fields. And just to flash quickly what these terms are, just so everyone is familiar, these matter fields and gauge fields they're literally Pauli spin matrices, and we'll get into the properties that we use later on. So we have this Hamiltonian. What is one way that we can conceive of it through a formal condensed matter standpoint? So if we start with a matter field, notably in this case, we'll start with the transverse Ising model, where we have degrees of freedom in spins on the vertices. The transverse field Hamiltonian reads on each edge, we have these two, the product, and we have an Ising coupling between them, as well as the dynamics that go around the edges. So the first step in gauging this procedure is to connect the nearest neighbors, not only with the Ising coupling, but also with a gauge field. And this is kind of reminiscent of the covariant derivative aspect of field theory. Now, the first step in going beyond this is to account for the interaction between the matter fields and the gauge fields. This is kind of like coupling your current to the matter field in field theory. And one thing that was done erroneously in a previous work, this was the independent study version of this talk, was in deriving this term, we included the matter fields in a way that, armed with only from the following source right here, we knew this was the final result and this was the final result. Using the figure kind of naively, we just kind of tried to figure out a way to include all of these matter fields with the gauge fields. This is incorrect, and there are 2 ways to fix it, both of which are thanks to one of Professor Wei's PhD students in the audience right now, Hiroki. So thank you for pointing this out, as well as the next remedy of this, which is a bit more formal. This is a bit more hand-wavy and is why I've been alluding to field theory, because now that we are working with gauge fields, we can use the background of field theory and thinking about things in terms of what's necessary, in terms of, right, we have the covariant derivative, the kind of algebra between the gauge fields, as you see here, the structure constant, which can be totally neglected for our QED case. It's just a U1 field. But we need to account for the gauge fields themselves in terms of their dynamics and how they interact with each other, barring any interaction with the matter field. And so in doing so, we need to have a term that involves only the matter fields, not and its derivatives potentially, but no matter fields. And so that's a very loose kind of hand-wavy way to show that we need not and ought not to include the matter fields in such a term. The more formal way is through conversation with one of the leading Fracton researchers, as well as Hiroki again. And this was something that we completely neglected to discuss in the previous talk on this material, which is that these terms commute. So the easiest way to see that they commute is to have them completely separated. None of these interact with each other. There's no, we don't need to think about the algebra of the Pauli matrices in any way. But even if they do overlap, so for instance, let's look at this picture here. So if we take this term and this term, there's no overlap, so we know that they commute because unless they share the same site, like here, this is one quivet and this is the other, which the Pauli matrices are giving us, they commute. So we don't need to worry about that. But if they do overlap, this anti-commutation can be shown that even if these terms do share an edge, as follows, that they commute. So that is if we don't include a matter field. However, if we do include a matter field, things get hairy. If we don't, though, and just have these two gauge fields, so here, this is the product of 4 X Pauli matrices, just like we had in the definition, and we have the product of Z Pauli matrices, just like in the other term. To simplify this proof, we can just note that moving these through things that don't commute, we don't pick up any sign flips. However, when they are sharing the same site, we pick up a commutation. But as those two minus signs cancel, we end up with the fact that two measurements on different sites like this actually do commute. However, the issue here is that if we, as we did naively, include the matter fields, this corner that's shared will end up leading the commutator to be non-zero. And so that kind of formally tells us that that BP term that we defined needs to not have a matter field in order for the construction that we have to actually reproduce the toric code, because in the toric code, those two terms commute. The next steps are to take some limits. So notably, the first thing that we do is take the Ising coupling limit, where this term in the original transverse field Ising model goes to 0. This is physically representing the paramagnetic phase. Secondly, going off of the field theory that we've alluded to previously, we need to integrate out the degrees of freedom corresponding to the matter fields. So the way that this manifests itself is this term goes to 0. It only depends on the matter field. But when a term depends on both the matter field and the gauge field, like this was kind of that AV, pseudo AV term that we defined before, now that goes to 1, and it's being minimized with respect to the gauge field. And now we have this term going to 0 because that term is 0. This whole term is going to 0. This becomes the actual AV term of the toric code. And this, note there's no matter fields as we corrected here, goes to the BP term automatically of the toric code. And so that's the procedure by gauging a matter system and getting the toric code. And what we're going to do is neglect the same derivation in terms of the X-cube model in favor of talking about a little bit more of the phenomenology of why is it called a fracton, and how do we reproduce that in the tensor gauge and field theory language. So the motivation, similarly to the toric code, was building this kind of quantum memory storage. So having memory storage that is not susceptible to error, things that are, the whole point of topological error protection is that because of the system, there is an inherent protection against error in the system. And the first, we'll talk about this a little bit more in the future directions, but the very first instance of this was very formal in terms of math and quantum information. And in the following years, it turned very favorable to condensed matter. And in that sense, the same gauging procedures of spin models, as well as the tensor gauge theory and lattice gauge theory that we'll cover soon, lended itself to describing these spin models. So what is this XQ model? This kind of stereotypical model of fractons. It's very similar to the toric code in the sense that we consider qubits placed along a lattice. In this case, we are in 3 dimensions. And so the terms here correspond to all edges of a cube having the X Pauli matrix, and with respect to one particular axis. So for instance, this is the x-axis. Everything else has a Z Pauli matrix. Likewise for the y-axis and the z-axis. And so making this kind of look like the toric code, what we can do is note that this, which is mentioned much more succinctly here, is very much like the matter field on the vertices in terms of the toric code. And these kind of almost no flux conditions along each particular axis are just like the plaquette terms from the toric code. And the way these fractons were kind of made up into reproducing this behavior that they saw in the fracton models originally was that there are different symmetries. So as opposed to it being one symmetry on a 2-dimensional plane, there are different symmetries along the different axes. So for instance, if we think about 3 dimensions and kind of chopping up our 3 dimensions into different planes, each plane could have its own symmetry. And so notably, if we have each axis having its own symmetry, there are different ways that a fracton can move. If we enforce only one symmetry along one of the axes, the particle can move about the plane that it's confined to. If we enforce 2, we'll end up with this thing called a lineon, which is something that we'll get more into when we talk about the dipole symmetry and why this phenomenology follows from dipole symmetry. Or if we can confine, or if we obey all 3 of the subsystem symmetries according to each axis, the particle is immobile, which is one of so these lineon with corresponding to dipole symmetry, as well as immobile charges, which we'll cover in the next few slides, is kind of the 2 stereotypical things of fracton phenomenology. Notably, one aspect of these lineons is that if we were to almost excite one of the lattice sites by placing an operator that would flip them, so if we note each of these terms along one of the axes, only 2 of them would be excited by a Pauli X along one of the axes. So for instance, if we think about the the y-axis, the 2 excitations would be along the terms that have gauge fields on the y-axis, notably this one and this one. And so leading to a lineon excitation. However, with a fracton, what we would end up doing is exciting with an X field, as a Z Pauli matrix. And in doing so, it would commute with all the other Z's, but not with the x. So we would create an excitation with respect to this term. And what ends up happening, we'll kind of, for a few slides, have this 3D picture to kind of reinforce this cube picture. But as we move on to include more of these excitations, we'll go to a kind of top-down 2D perspective of this. So what's happening here is each of these 4 neighboring cubes share an edge with this new excitation. And so because of this term in the Hamiltonian, they get excited. As we apply more of them, we're kind of spreading out these excitations. And the reason for that will be clear in just a second. Note that now that 2 of these edges are shared by these 2 cubes, we've gone to like a doubly excited state, or in the sense of kind of a flip operator back to its original. Once we kind of apply more of them so that there's this separation between these excitations we'll see in the next slide are what are known as the fractons. Because if we were to just consider one of them and we were to try to move it a little bit, there really is no notion of the word move in these fracton theories. The only thing you can do is create more of them. And we'll see that this follows immediately from dipole symmetry later on as well, that if you were to apply 1 and you think maybe that you would just end up moving, because of the exciting all the neighbors, the only way that you would be able to actually move a fracton is to create more of them. And so this fractalization is the reason these excitations are called fractons. And so that kind of concludes the spin model picture of fractons. Note that we haven't gauged the matter field like we did in previous work. But the next aspect of fractons is really with regards to gapless models. So these spin models are entirely gapped because they include these excitations. But when we're thinking just about the gauge fields, kind of a new framework was needed. And it was really due to Pretko, as we'll talk about later in the gauge and the tensor gauge field and the fracton field. But it really had to do with a formalism that was not clear at first. There are these implicit formalisms in the tensor gauge theory due to things that happened much longer ago in the 1970s. So going off of the Wilson lines and Wilson's kind of lattice system, there's this picture where we can take gauge fields and put them on a lattice and study their dynamics using the formalisms of condensed matter. So just as a refresher, the gauge system that we're going to be looking at, and we'll use the toric code as an example in a moment, is electrodynamics. One way that we'll be able to motivate the toric code is to say that it's like QED on a lattice. And so QED, quantum electrodynamics, so it makes sense to just get ourselves a framework in the classical sense. So we know that we can take these 2 Maxwell equations, use some vector identities to get these expressions for the fields. And we know that because of the gauge invariance of the U1 symmetry in electrodynamics, we can choose to fix a particular gauge. The one that we'll choose is sometimes called the Hamiltonian gauge for reasons that will become clear in a minute, or the temporal gauge, where the temporal part of the gauge field is set to 0. And so that nullifies this term, and we end up with the E being the negative time derivative of the gauge field. And as we'll use the flux more in this discussion as opposed to just the B field itself, using Stokes' theorem, we can write the flux as the kind of line integral over the gauge field. And so one of the aspects that we need to account for when we're doing kind of lattice work is that these gauge fields they're not unbounded. They have some kind of symmetry that they need to respect. And in particular with lattice QED, the symmetry is U1. And so U1 is kind of the gauge group of a circle. And so these variables of the gauge group need to be bounded in that sense. So they're an angular quantity. And we'll focus more on this a bit later, but we define the positive direction to be along the x-axis, the negative to be in the other direction. So right is positive, left is negative, up is positive, down is negative. And note we generalize here this here because we're now placing the gauge fields and the corresponding kind of what we'll see in a minute is like the conjugate of the gauge fields on the lattice. So on the lattice, we have these two indices. One of the most succinct ways that I've uncovered in deriving a lot of these lattice Hamiltonians is to go from almost a very classical mechanics perspective. So if we think of the gauge field as now our canonical variable, so like A is now our X position, taking the time derivative of that is like the velocity. And the velocity has this relationship with the momentum in the sense that, you know, we're taking the mass to 1 at the moment. We have the kinetic energy being like the dot of the A fields, and the momentum with this kind of field theory definition here being this. So that's what we mean when we say the electric field is like the conjugate to the gauge field, just like the momentum is conjugate to position. And so either plugging directly in this definition that we already knew, we have, and taking again the permittivity of space to be 1, we have that the kinetic energy is 1/2 of the E field squared. And we can also take into account that when we think about divergences and curls in a lattice perspective, it really is just summing the things across the edge. So for instance, in the sense that the curl is like a kind of integral over the circumference, it's now just the sum of the edges. And we're taking into account this definition of up, right, down, and left. And if we think about the potential energy from almost like a inductor kind of juxtaposition here, using the fact that the B field is still the curl of the A field, and we know that the curl is equal to the flux. So defining this with this perspective, we almost have what we'll use as a potential energy from the gauge fields, but we need to take into account that the gauge fields have some periodicity. And so using almost like a Bloch's theorem argument, we need to have periodicity in the potential energy as well, because it depends on that. And we can also justify the previous kind of classical mechanics argument by taking the small angle approximation, because we know that, right, that doesn't exactly equal 1/2 the flux squared. There's that 1, right? There's the 1 in the small angle of the cosine. But when you define a Hamiltonian, you're free to add a constant and none of the dynamics change. So we have the following kind of construction of the Hamiltonian. What we need to consider now is we've said that there's this electric field coming from the gauge field, but where does the electric field come from? We know that there's this kind of construction between charge goes to potential, goes to electric field. So if there's some E, where is the charge that's creating it? And we're going to locate that on the vertices in the following way. If we take the divergence of the E field, the divergence, like the curl, is the kind of sum along the edges. The divergence is the sum along the edges that connect to a particular vertex. So if we take the divergence at M, the divergence is like the sum of the edges that connect to M. So here, as opposed to the curl, we had different indices. Now each of them have an M. And so using that kind of construction, right, we can't just put the charge into the Hamiltonian. We need to have an energy associated to that charge. Using kind of a Coulomb argument, where we have the charge squared over R, where R can kind of be negated at this point because we're working on the lattice. We have a prefactor and the charge. So we end up with this formula for the Kogut-Susskind, who kind of modified Wilson's work on lattice gauge theory to make it into a Hamiltonian formalism. So at this point, this was in the independent study phase of this project. This was a place where I really struggled to understand how the lattice QED is a motivation for the toric code. The only thing we do here is just replace the A's with S's, because we have, magnetic fields and gauge fields now, so that'll be quite confusing. So the toric code is now just going to be defined with S's and P's instead of A's and B's. The way that we make this identification is to compare this Hamiltonian to this Hamiltonian. Note that we have 3 terms in the Kogut-Susskind QED Hamiltonian and 2 terms in the toric code. And how do we make this relationship between the 2 of them? We already had this kind of condensed matter, classical mechanics argument. And so as we quantize that, what do we do to these gauge fields and E fields that make this sound? And the reason we're doing this is because it relates to that commutation of the terms in the toric code. So we need to know which of these 2 terms commute with each other, because that's how we're going to determine which of these 2 terms we keep and which we discard with. So doing this kind of canonical quantization argument, if the A coordinates corresponded to our position and momentum, recall, was the negative of the E field, we now have this commutation between the 2 terms. That is not equal to 0 though. So one of the things that we'll notice here is that this, when we take the small angle limit, has a squared in it, and this has a squared in it. And so what we end up doing is making the ansatz that if one of those is going to be negative and the other positive, if we can square this so that it's E squared, A squared, and what's I squared, -1. If we have one of those terms being negative, which we end up doing if we do the same overlap argument that we did with the commutation, we have the following, where it's those 2 things are going to add together to give us the commutation that we had from the toric code. So our ansatz is that this cosine squared term, or rather the flux squared and the divergence squared, are going to be those 2 that commute. Notably, if we take this, right, we have the divergence on a vertex and the curl around the plaquette. These are both the same sign, where these have opposite parity. And so those are going to give us the commutation relations of -1 and 1, which add to 0, just like the commutator of the toric code. So now that we have that kind of loose equivalence between the 2 of them, we can do away with the that kinetic term that we had, which was previously we kind of just made the error in thinking that we just do away with that term where it wasn't justified. So now we have this kind of Hamiltonian with only 2 terms. So we've got 2 terms and 2 terms in the toric code. But how do we make the identification? Like, is this the AB or is this the BP, or what's going on here? So if we make this identification between the gauge fields and electric field with the matter fields, let's just say make the following ansatz that the gauge field, the Z gauge field, is equivalent to the exponential of the gauge field on the lattice. By doing so, if we, this is what the plaquette term is in the toric code, we add this up here, and by using the property of exponentials, we have this, and we know that this was the lattice definition of the curl, which equals the flux, and by using the kind of small angle or Euler formula here, we end up with the exact term that we had previously. Similarly, but we need to kind of account for the Z2 symmetry of the toric code. If we make the following ansatz, do the same kind of properties of exponentials, use the lattice definition of divergence, and have charge, in order to account for the Z2 symmetry of the toric code, right? We have either spins up or down, there's that symmetry. We're only going to allow the charge to be either occupied or not occupied. So either the the vertex has no charge or it has just a single unit of charge. In doing so, we end up creating, and that's hence this kind of inclusion of the pi here. If this is 0, it equals 1. If it's 1, so charge is occupied, it's -1, which is exactly the eigenvalues of the toric code. Either it's 1 or -1, just like the Pauli matrices. And so with this kind of construction, the whole reason, this was kind of a corollary almost, that we said, oh wait, now that we know this kind of lattice formalism, we can get to figuring out one of the things that really stumped us with the independent study version of this. But the main objective here was to get a grasp on a lot of the things in the tensor gauge picture, which was kind of this huge revolution in going beyond the spin model picture of fractons, which was to explain the phenomenology which we saw before in terms of kind of a fractalization in terms of dipole symmetry. So unlike the toric code, which just had the U1 symmetry, which corresponds to a total charge number being conserved, this is an example of total charge being conserved. We have a positive charge and a negative charge, and these arrows are like the positive charge and negative charge can move. And we know that that is conserved because the charge, as we had earlier, the charge is like a total divergence of the E field. However, in terms of fractons, they knew that they had this kind of fractalization, and the way that this was envisioned was actually thinking about dipole conservation and how are you going to get dipole conservation from like a Gauss's law constraint like we had here. So the way that this was envisioned was, instead of the gauge invariance of a U1 symmetry, increasing the order. So when I say increasing the order or a higher ranked object, a scalar is a rank 0 object, it has no indices. A vector is a rank 1, and a tensor is a rank 2. And so, as we'll show soon, the increase in rank is pivotal and necessary in order to derive a conservation of dipole charge. One thing I want to note, I mentioned some of the things that were cut out. Professor Wei's PhD students helped me immensely in going back and forth between these two objects. It was not clear to me how gauge invariance implied Gauss's law, and that can be found in the thesis as well. So now that we have more than charge conservation. We still have charge conservation, but defining something like a dipole and using a kind of integration by parts, we end up with a very similar argument here, where the charge ends up being the total divergence. So, boundary term in the total integral, we have the same via an integration by parts with this x operator. And now, why is this dipole moment? Why does it end up giving us the same phenomenology that we saw when we were working with spin models? The first thing to note is that we don't have to have a total fracton. We don't have to have a completely immobile term. But if we have some non-zero dipole moment, if dipole moment is still conserved, then charges aren't free to move around like this, but they are free to move around together. So for instance, if at some time t equals 0, we have a non-zero dipole moment, at some time t equals delta t, we still have to have the same dipole moment, so an arrow pointing in the same direction. So this is just like the lineons that we saw before we kind of covered the full fracton phenomenology, where two subsystem symmetries are respected. However, if instead of a constant but non-zero dipole moment, we instead have a zero dipole moment, then this is a way that we can, because there's no way to move any of this, right? So envision trying to move naively one of these. This is not this is not a zero dipole moment. So here we have something, unit, let's just say unit length going to the right, unit length going to the left, up and down. So this altogether has a 0 dipole moment. By moving one of them, we violate that. Now there is a, considering this the origin because it was 0, we now have a vector 1 and 1 going up and to the right. And so the kind of naive way that we would try to remedy this is, okay, let's add a negative charge down here that would point the, as a resultant dipole interaction, point down. Okay, that would return us to a 0 dipole moment, but now we would have three negative charges and only 2 positive charges. So it's much more subtle. We end up needing to just, quote unquote, moving one of these fractons, we end up creating 2 in the process. We need to, instead of naively having this down here to respect the dipole moment, we also have charge conservation. So we need to add this in a more subtle way. So this is how this kind of higher rank order gauge fields and electric fields necessitated dipoles, or gave us dipole symmetry, which described the phenomenology that we saw in the spin models. And using this tensor gauge picture, there's this kind of revolution in the sense of how we get this in a field theory perspective. So kind of viewing this from almost a classical field theory perspective, in the sense of using Noether's theorem and continuity equations, we can have Noether's a Noether charge, which is a constant of motion due to a symmetry in a particular Lagrangian. We have a Noether charge in the U1 case, which is a symmetry like the field transforms with an exponential, and the symmetry reads like this. The electric charge is the conserved Noether charge here. In the dipole case, it's not clear at first where this kind of continuity equation would come from. And recall that if we see here, this is a rank 1 object, this is a rank 0 object. And so in order to have a Noether charge, which is rank 1, it's going to necessitate us to have some kind of rank 2 object as what we're taking the integral of with a continuity equation. And so as opposed to the standard continuity equation, where each term has like a saturation of indices, we're going to need something where we have a higher rank spatial current. And so this is kind of what we need in order to have dipole moment. And this was pointed out by an author of work that was done much earlier in terms of defining things called polynomial shift symmetries, which is like, it's similar to a U1 symmetry. We have this kind of exponentiation of the field, which in a small limit, we can Taylor expand to get the following symmetry. And so in order to have a continuity equation that gives us conservation of dipole moment, we need to include a new symmetry, this polynomial shift symmetry, but we also need to update the Lagrangian. So the same Lagrangian that would give us like something like a Schrodinger Lagrangian that would give us a conservation of charge due to a simple rank 1 U1 example like this. We need something with higher derivatives, notably the spatial derivatives. Again, this proof is really does not lend itself very well to slides. It is enormous, and I seriously thank Yabo for helping with this, Professor Wei's PhD student, in the sense that one of the main kind of authors that I mentioned before was Pretko, and he kind of went beyond this spin model approach to viewing things in this new formalism of tensor gauge theory. It was stated very early on in one of the landmark papers that the symmetry that is needed to have this dipole conservation is as follows. And it was not clear at first glance how that symmetry of the fields leads to dipole conservation. And so that's why it took a substantial amount of work to prove it. It was warranted because it was kind of stated without proof, but it was also totally justifiable that the author didn't prove it, because the main example of, or the main accomplishment of this work was much broader in scope. In fact, what it ended up doing was creating not only kind of an ungauged Lagrangian, which is just, the actual explicit form of this, it created a gauged Lagrangian. So he had this ungauged thing that respected dipole symmetry. He gauged that Lagrangian to have something that transforms with the exact polynomial shift symmetry. So with a kind of full gauge theory in hand, an intense effort from the high energy community began as well, in the sense, for instance, Professor Xiujin Xiao at Stony Brook now has been doing a ton of work with Natty Seiberg, as well as many others, and it's delving into very, very formal topics, trying to understand what the quantum field theory is. Is it formally grounded? Does it have kind of causality? Like there are a lot of things that need to be sussed out. So in future work, because we thought it was so necessary to derive this dipole conservation fully, a lot of what was left in that paper remains to be worked on, and so that's what we'll be doing in the future. Notably, some of the ways that the covariant derivative come up is not quite clear. Like, for instance, in a field theory and gauge field theory procedure, you need to respect how the gauge fields transform. So notably, how does the covariant derivative take into account all these transformations of the gauge field? The next future direction is really what inspired this work, actually. The gauge fields and the gauge field picture of gravity was what I was working on years ago when I first discovered fractons, because it was cited, the particular paper I was working on, which was viewing gravity as a gauge theory from different symmetry algebras, using these symmetries. A previous PhD student of Sasha Abanov at Stony Brook used those symmetries to construct a symmetry algebra, much like the Poincare or the Lorentz algebra, and gauge that algebra, much like I did in previous work with general relativity and algebra, and use that to create the exact same effective field theory that people like Pretko are working on. And so this is beyond the scope of what we've done so far, in the sense that we've kind of covered these spin models as well as the gauge field, the tensor gauge perspective, whereas this formalism uses the kind of polynomial formalism way back in the kind of inception of fractons, which was very quantum information mathematical. And so one of the things that we would be using in that is actually a previous master student's work of Professor Wei, who wrote a brilliant master's thesis who used a lot of these polynomial shift symmetry formalism. And lastly, it's only fitting that the way that Ha came up with these fractons was motivated by very practical purposes. How do we store memory in a quantum computer that's kind of impenetrable to error? It's only fitting that now that it's been a decade and this kind of theory of fractons has been really formally grounded, that we start to look into ways to realize these experimentally. And there's been a ton of recent work in ultracold atoms in realizing these. In particular, in three-dimensional optical lattices, we can mimic the same kind of systems like the XQ model. The XQ model was a three-dimensional lattice. And so aiming at kind of simulating these systems in a quantum information context, the work in terms of many body localization, which is and thermalization, kind of have led to realizing dipole conservation systems in three-dimensional optical lattices. So that's kind of the next step in terms of someone realizing these systems experimentally and potentially putting them to their originally intended use. And so I just want to thank everyone, particularly Professor Wei and Yabo and Hiroki. It was very fun. I'm sad it's over, but it was so fun to do all these things, and I couldn't have done them without you. And likewise, thank you to Professor Canonical for serving on this committee and being great for professors in our respective classes. And of course, thank you to everyone who supported me along the way. And yeah, I can send these slides in the chat as well to have applicable reference links and such. I'll just leave on the outline in case that helps spark questions.
So I have a question. One thing I was unclear on is where does previous work end and where does your work begin in here?
Say it again.
So you gave a summary of a lot of existing works, toric code, X cube model. So is there some part of this which is also your kind of original contribution?
Yeah, absolutely. In terms of, let's see here. So in terms of it was definitely an error on our part to kind of read into this, but it was a lot of the main contributions are in terms of things that justifiably so, because most of these references are way beyond the scope of these derivations. But a lot of them were, for instance, this figure in this paper was used to justify the following inclusion of terms in the Hamiltonian, where it wasn't explained, and because of the where this term came from, led to the following error. And so correcting that was entirely novel, as well as kind of there are, let's see, so in terms of like kind of reducing the Kogut-Susskind Hamiltonian to the toric code was done very briefly in the following reference, in the sense that it was almost done with this equation and this equation, and that's really it. Kind of trusting the reader to go to take these things either as gospel or to know where they came from. And so using this new lattice gauge theory formalism and understanding where those come from, as well as why those two terms are the ones that we need to do, was novel in that sense, as well as it was kind of, and I looked far and wide, but in order to kind of go between these two, gauge invariance and Gauss's law, all of the fracton work was kind of, even Pretko's own work was, they were just stated as these exist. So there is this kind of correspondence. We need this specific symmetry. For instance, this was quite substantial from the original slides. The kind of justification for a lot of these equations was kind of stated almost in a line, and trusted either that the reader did this on their own, which is the only way that we saw to move forward, or was just taken as trust a priori. So the novel aspects are with regards to the correct form or the correct derivation of the BP term and the rationale for it, viewing the toric code as QED, the correspondence between gauge invariance and the corresponding Gauss's law, whether it be in the standard way that we know, like the normal kind of, the gauge field is a vector, or in the gauge field as a tensor, both of those, as well as justifying the symmetries in a field theory perspective because they give us dipole conservation.
I want to ask questions.
Yeah.
So you use these e square and a square the commutation to
Yes.
justify, and then you say it's -1. I think this is maybe a bit misleading in the sense that it's not mathematically correct in the sense if you can consider the commutation of the square of the two operator, it's not necessarily just squaring the I. So I know you try to make things very intuitive, but at that part, I feel it's not rigorous, and yeah, this is my comment on that particular part.
So in terms of like
if you go to the next slide, you have the e square.
Right.
I think that's mathematically that's not correct.
So if you were to take, write out the,
for example, yeah, if you consider, yeah, that you can use the formula to reduce those to commutation of E and A, but I don't think it's going to end up with commutation of E and A square. So you have to, I mean, stating this, you have to be careful checking the math.
Okay.
But I know you're trying to derive all the steps and make it really intuitive. But sometimes in saying that, you could say, well, you have to be paying attention to the mathematical rigorous there. That's why. That's my comment.
Actually, let me check really quick.
If you cannot find it, maybe you can check it later, and then it's that commutation relation is not -1.
Okay.
Yeah. I think that's you have to fix that.
Okay. Thank you for pointing that out. I thought I had it.
And then then get to use some typo. It's conversation. You wrote it as conservation somewhere, but that's fine.
It's probably in the.
And maybe this is a question. Maybe it should be asked by Dominic. But I want to ask. You mentioned a co-atom simulation, but the XQ model, for example, has this cube interaction that involve all the edges in the cube, 12 edges. So there will be 12 body interaction. How would it envision that could be simulated?
Interestingly enough, I believe it's almost kind of similar, and I wonder if Professor Cano can chime in as well. I can go to the citations as well, but it seems like these realizations were done with kind of overlapping honeycomb models, in the sense that a honeycomb lattice has 6 vertices, and overlapping them, I think, was the way that this was done. Let me refer to these.
Are they trying to engineer the Hamiltonian, or are they trying to really using the sort of active interaction?
I believe the whole Hamiltonian.
Because to construct Hamiltonian of 12 body would be difficult unless they're using some perturbation theory to start with maybe nearest neighbor, and then you do the higher order. Yeah. Of course, this is in your for the future, but do you have any idea that could be done? Instruction. So they start with 3 body, and some kind of density interaction.
Yeah, so they're staying. let's go to this one. Appendix of this, I believe, would be more helpful.
I think this one would use more of active sort of
Right.
gate operation.
Yeah, you're
Heavy
right.
measurement. Yeah.
So yeah, there's definitely sublattices going on.
Maybe in the interest of time, I would suggest you can write some of the explanation, maybe in the thesis,
Okay, yeah.
something like that.
Would you like me to turn it over to just the committee?
Do you have any question, Dominic?
I still have just one very naive question. So the term fracton seems to be used in conjunction with the term fractal. So I mean, what is fractal about fractons? I mean, you make this connection in the introduction as if it were given, but I would like to know what is fractal about fractons?
In the sense that even in the gauge model perspective, in applying kind of trying to get a specific excitation to move. So let's just try to move a particular excited box, by applying these X Pauli matrices to another location. The only way to do so would be to excite other nearby terms because of the kind of shared edge of the other box. So in moving one fracton, we create others in doing so. So let's just say we move this over here. In doing so, we've created two additional ones. And that's
it seems to me that this term fracton comes from fracturing. So you're breaking something up maybe, or recreating, but I mean, there's no self-similarity here or any of those concepts like Lyapunov exponent and so on from chaos and fractals that I would recognize, right?
Yes, I think what you're referring to is actually what was just in that condensed matter perspective, the Serempinski triangle, which was much more noticeable in the very original work of Ha. So as I understood it, it was almost totally due to kind of respecting dipole symmetry that you needed to create more charges and that's the only way that I view fractons and the fractal adjective. But I believe it's more concrete than that, in the sense that doing things in the polynomial formalism led to a much more geometric structure that you're referencing.
So are there any bifurcations, for example? Or?
Yes, specifically in terms of
There might be a picture from Ha with the fractal structure of the logical operator.
and actually
Somewhere.
what Sifan did in his thesis was exactly what you're referencing, Professor Snable. Let me see. Actually,
I don't think he called these fractal. It was later, but it's mainly due to the
This is now the PhD advisor of Susan Stone, the previous master student, and led to so what I'm referring to is his thesis title was called bifurcating or decompose.
Okay.
So let me. This is what we're looking for.
Yeah, there's one picture on them.
Right.
That's the,
It looks fractal.
yeah. That's another picture, 2D picture.
So an application of a single operator creates 4 at the corners. Repeated application. Separate the 4 corners, kind of like the, so I think it amounts to the particular geometry that I chose being like this figure wasn't from anything. It was just, I thought it was easier to make personally. So it's based on the kind of 3 nature of this, perhaps it would have been better to have a let's see here, a kind of almost a triangle, and it would have kind of created a more noticeable fractal structure, because that's exactly what they're doing.
Maybe also if you had kept going more than once, then that's what you need, right? Because
Yeah.
you've only done it one time, so you
Yeah.
can't see the structure.
Exactly.
Okay, I mean, I'm satisfied with the answer for now.
Yeah, I was wondering, Jason, if you could, I don't know if this is too broad of a question, but if you could say anything about how fractons could be used for quantum error correction.
Yeah.
This is kind of like a motivation for this. Yeah.
In the sense that there's more, and it was I just closed it, but the ground state degeneracy of fractons is much larger than the toric code. So because of this fractal nature of things kind of propagating like that, the ground state degeneracy is exponential, as opposed to the ground state degeneracy of the toric code. We won't be able to see it. There are slides in the independent study talk on this, but based on the kind of almost like stabilizer errors in a toric code, there are really 4 particular ground states for a particular system, and so those 4 ground states and 2 qubits, as opposed to that, is limited. Of course, Google and Microsoft and IMB are having a field day with it, but the idea is that there will be kind of linearly, or not linearly, exponentially increasing degeneracy of the ground states, which is just further protection against errors because of the multiplicity of the ground states.
Yeah, I see. That makes sense.
I think it's very difficult to control these fractons because the structure of the logical operator is really not simple.
Yes, error.
To use these degeneracy, I think it's very difficult. It's maybe the motivation is that these excitations don't move, so they may be stable. If you have information, it won't change.
So maybe as a memory, maybe the bigger application will be as a memory rather than error correction.
Right.
Got it. Okay, great. Are there any more questions from the audience?
Okay, let me.
Jason, maybe you can create a breakout room and put the 3 of us.
Yes, I am going to.
Oh, okay.
Yeah, I just made Professor Cano the host, so everyone who's not the committee can just leave. And
so maybe everyone who's not. Yeah, maybe we can ask the audience to leave, and then we put Jason in waiting room.
Oh, yeah, right. That would be fine as well.
Don't forget to turn off the recording.
I think I just oh, it is still
you have to turn on.
I think Professor Cano